Micron is a handheld instrument that actively cancels hand tremor for microsurgery. Micron can also aid fine manipulation for handheld OCT imaging, patterned laser photocoagulation, and membrane peeling. Micron incorporates a miniature micromanipulator and embedded electronics in a handpiece. For the micromanipulation of the tooltip, 6 piezoelectric linear motors, called squiggle motors, are used. The handpiece is also equipped with 2 sets of infrared LEDs for tracking of both tooltip and handle motion. For various applications, any tool, such as a needle or a laser probe, can easily be installed on Micron. The micromanipulator adopts a miniature Stuart-Gow platform configuration, and its dimensions have been optimized to tolerate a side load of up to 1/4 of a newton at the surgical incision point. As a result, the manipulation provides 6 degrees of freedom motion of the end effector within a cylindrical workspace 4 mm long and 4 mm in diameter, while allowing for a remote center of motion at the point of entry through the sclera. The Micron system consists of 3 parts: the handpiece, the optical tracking system, and support electronics. While a microscope is required for microsurgery, any microscope can be used, since Micron functions independently using its own optical position measurement. In addition, when the system is interfaced with CCD cameras within a microscope, image guidance from the CCD images can be utilized for visual servo control of the tooltip. The system is also equipped with an augmented reality display or visual overlay system to deliver visual cues to the operator. Cues such as the region of interest, identified blood vessels, and the distance of the tooltip from the retinal surface can be presented within the microscope view. For control, Micron senses the position and orientation of the tooltip and the handle using the optical tracking system. The position feedback is then used to control the linear motors in the micromanipulator. As a result, only the voluntary motion of the handle is delivered to the tooltip, while undesired motion, such as hand tremor, is canceled. This sample video clip demonstrates how Micron operates during a simple pointing task. In unaided operation, the motors are disabled and the handpiece functions as a conventional rigid tool. When cancellation is enabled, the motors are actuated to keep the tip stationary even though the operator's hand is moving. This creates the effect of the tip seeming fixed at a point in space despite the motion of the handle. It can be seen most clearly by observing the actuator motion during cancellation. Active tremor cancellation is the primary function of Micron. Using this function, Micron suppresses undesired hand tremor while preserving the operator's voluntary motion. Involuntary motion during micromanipulation can be identified at a specific range of frequencies, for example, from 7 to 14 Hz. Hence, by applying low-pass filtering on the motion signal at the tooltip, we can stabilize the tooltip motion while preserving voluntary motion at, say, frequencies below 2 Hz. Micromanipulation can be improved even more by applying a shelving filter, which provides a sort of relative motion scaling by attenuating the tip motion to 1/3 of the hand motion within a low frequency band. We evaluate Micron's ability to improve accuracy in tasks that resemble microsurgical manipulations. The test target here is a rubber slab with a circle 500 microns in diameter. As shown in the video clips, smoother and more accurate circular trajectories are achieved by active canceling algorithms, whereas unaided manipulation produces a much shakier trajectory. The next task is attempting to hold the tip stationary inside an artificial eyeball phantom, which more closely approximates vitreoretinal surgery by imposing a fulcrum constraint at the point of entry through the sclera. The trajectories of the blue tip are presented as black in the videos. Micron can be seen to reduce hand tremor significantly during vitreoretinal microsurgery. Micron can also be utilized in handheld scanning for intraocular optical coherence tomography. For handheld OCT imaging, a single fiber OCT probe is integrated with the Micron system. It can detect retinal structures up to 3 mm below the surface with Micron resolution. The capability of fine manipulation in Micron enables multidimensional scanning. First B-mode scans are achieved by scanning the OCT probe laterally. In addition, with spiral scans of the tooltip, en face reconstruction is also possible. Finally, by accumulating zigzag scans used for B-mode imaging, 3D structures can be reconstructed. The stabilizing function of Micron is also used for handheld OCT imaging. We performed A-mode and so-called M-mode scans in rabbit eyes in vivo. For testing A-mode scans, a hold still task was adopted. For M-mode scans, the OCT probe was scanned along a line of interest inside the rabbit eye. The resulting trajectories over the time of scans and corresponding time frequency analysis are presented. For both types of tests, open sky and in vivo, smoother trajectories are attained with Micron stabilization. In M-mode scans, we also see smoother trajectories along the scans with the aid of Micron. As shown in the results of the time frequency analysis, the motion signals corresponding to hand tremor are significantly reduced in the low-pass and scaling control modes. The next application of the Micron system is automated intraocular laser surgery. Laser photocoagulation is a common procedure to treat retinal diseases such as diabetic retinopathy, retinal detachment, etc. Using Micron, the treatment can be automated by interfacing with the operating microscope and CCD cameras. During automated laser photocoagulation, the operator holds the handle still. The tooltip is automatically deflected to burn predefined targets via visual servoing of the aiming beam emitted from the laser probe attached to Micron. In addition, the distance of the tooltip from the retinal surface is automatically regulated to maintain a specific height using a virtual fixture scheme. Since the eye moves in its socket during intraocular operation, the retinal surface is also tracked in real time to maintain anatomical registration of preoperatively planned targets. Moreover, the tracking feature enables programming to avoid coagulation of critical structures such as blood vessels or the macula. This clip shows a demonstration of automated laser photocoagulation in the eye phantom. In the video, the green line shows the tracked blood vessels. The circular targets were defined along the circumferences of multiple circles of diameters 1, 2, and 3 millimeters, with a spacing of 600 microns. The upper row presents unaided operation with fixed repeat rates of the laser from 1 to 2.5 Hz, such as are typically used in clinical procedures. The bottom row demonstrates automated operation with Micron. For automated operation, various targeting thresholds were used from 50 microns to 200 microns. When the aiming beam approaches a target and is within the specified targeting threshold, the laser is automatically triggered to burn the target. The automated system significantly improves the accuracy of laser photocoagulation, showing over 50% error reduction compared to manual operation. In addition, the automated laser photocoagulation yields regular sizes of burns by maintaining a consistent depth of the laser probe from the retinal surface. For more information, please contact the Surgical Mechatronics Laboratory at the Carnegie Mellon Robotics Institute. Thank you.